So hey folks, hope you've been alright. In this video what I'm going to do is I'm going to continue the discussion on graphs in motion that we have started. So in our previous two videos, I guess, we have talked about graphs pertaining to the coordinates t and x, that's position versus time graphs. Using that, we have worked on v versus t, or velocity versus time graphs, and using this, I intended to work with a versus t graphs, which are acceleration versus t. We're going to do the same thing as we did with x versus t to v versus t. We're going to use this information to get acceleration versus time graphs. So essentially, we're going to continue what we already know, but with just different words. So this video is going to pertain to acceleration versus time graphs and how we make sense of them, how we make sense of velocity versus time graphs, how do we use velocity versus time graphs to determine a versus t or acceleration versus t graphs, and we'll also touch and refresh your memory on x versus t graphs as well when we're talking of these two graphs. So let me get rid of this for the moment and begin our discussion. So just a small recap, I guess. A recap never really hurts. What we know from our previous discussion is the fact that if you're given a x versus t graph, which is a position, this is position, versus time, and you choose to measure that, say, in seconds, and you choose to measure this in meters. So I'm sticking with the SI units, but it's a good thing. And say you have an x versus t graph, which goes something like this. So the same thing as what we have been dealing with previously. We use this information to get another type of graph, which we call the velocity versus time. So that's time there, velocity there. Say I want to measure velocity in meters per second and time again in seconds. Using this piece of information, we firstly divided the graph of x versus t into many parts, those parts that held a constant slope. And the reason we were bothered about slope is because velocity came out to be d of xt by dt I cap. So this is what velocity came out to be, or simply velocity in its scalar sense, or in the sense that we're going to use, what came out to be d of x as a function of time by dt. So that came out to be the derivative of this x of t function. So all we need to do is to find the derivative of the function at different points, and using that, if we plot those derivatives, we get our velocity versus time graph. So the reason we bothered about slopes is because slope is nothing but the derivative or the tangent, or basically the gradient of different parts of the graph. So in the first part of the graph, well, it points, say, in theta degrees up north, or in the positive x-axis. Using this piece of information, we established what tangent of theta is going to be, and we plotted that there up to the same point of time where this graph merged into this part of the graph. So we drew that constant line because this slope is constant, and I believe what we got from the last discussion was the fact that this slope came out to be, I guess, 2.5 meters per second. That means it's going in it's traveling 2.5 meters in the y-axis if you choose to go 1 second in time. So that's what it means. That's the tangent of theta. We worked the slope again for this part, and since this part is sloping in a negative direction, that's a sloping downward, this meant that the slope in this case has to be negative. We ended up finding was that the slope came out to be negative 10 meters per second. That is to say, if you choose to go 1 second in the positive x direction, you end up going negative 10 meters in the position coordinate. So that's how you would make sense of this graph there. This segment of the graph meant that the slope is 0, so that meant slope equals 0 or velocity equals 0, and we ended up plotting those as well. So from this corresponding to the first slope of 2.5, we plotted 2.5 on a y, and we plotted that on v versus t. We then moved on to, well, this doesn't look like negative 10, but say this coordinate here is negative 10 meters per second. We plotted that in a second time, interval of 1 second. This is 1 second from there to there. And then again, when it reached this component, this part of the graph, we knew that the velocity was 0 because it's neither sloping upwards nor is it sloping downwards. That meant the velocity was 0 throughout the 1 second as well. And when we moved in the last part, or the last branch of time, we ended up finding that this time was that this time the graph pointed in the positive direction, or it sloped in the positive manner. That is to say that the velocity was then again positive, so it was some other velocity, like say that. So you got this broken sort of graph of v versus t of that manner, this, that, this, sorry, this at 0, and this back again. So it was a broken graph, and we tried to make sense of this again. But you would notice that for most intervals of time, the body is holding a constant velocity. This means it's a constant velocity. So does this mean that, so velocity, and even this 0 slope in v versus t, it meant constant velocity. Here it meant constant velocity again, here as well. So just like the fact that we said that this part of the graph corresponded with constant position right there, this part of the graph meant this, this, and this, and that meant constant velocity. So every time the graph doesn't move in either of the y coordinates, that is in positive y or the negative y, we mean that the graph is constant, that the velocity or whatever is being measured on the y-axis is constant. Here it's velocity, so that meant it's constant velocity in these horizontal bars, and here it meant, well, constant position, because that's what we are measuring on the y-axis. So we are now at a situation where we have constant velocity, and that's it. But if we further move on to discuss different parameters that are involved in motion, well, we know that velocity is not the last thing, or the concept that we discussed at the end. We have one more concept to discuss, and that's acceleration, which many people also talk about. So let me get rid of that and define formally what acceleration means. To many of us, I guess we will be familiar with acceleration, but it never really hurts to describe it once again. So at this point, I would like to start by drawing out an analogy between velocity and position. So we know velocity, in its scalar sense, comes out to be the derivative of the position versus time. And just like that, it becomes a function of time as well. So like position, velocity becomes a function of time. Like it should have been, because velocity was changing with different times. At some point of time, velocity was plus 2.5. Other points of time, it was negative 10, and so on and so forth. So you have different velocities at different time. And this is what this change is what this function of t encapsulates or takes into account. So let's get rid of that. Right. So just like that, if we talk about the derivative in velocity, we get a new concept called or a new parameter called acceleration. So it's very similar as what we did with velocity and position. So acceleration basically comes out as the change of velocity, or better still, it comes out as the rate of change of velocity. So rate, whenever you say rate, you always mean rate in time. So that's why you have this rate that you're measuring in time, because of the fact that you're differentiating it with time. So that's what it means. Acceleration comes out to be the rate of change of velocity, and velocity comes out to be the rate of change of position. And so that is what I meant by drawing out an analogy between both these concepts. Now, you can also stop here if you want. That is, you can go, if you choose to go, if you don't choose to go further than acceleration, well, that's good enough. But many times people also discover, or they also talk about concepts like jerk as a function of time, which comes out to be the derivative of acceleration. So it's like you take a position coordinate or a position function, you take its derivative once, d by dt of that, you get velocity. You take another derivative of that, you get acceleration. And if you choose to go a bit more further than that, you take the derivative of this acceleration and you get jerk. But for most of our discussion, we will be limited to the first three derivatives, or the first two derivatives of the first three quantities. We will not consider jerk for the moment, because that just gets more involved. Anyway, the discussion is very similar to what we have done so far. So say we have a velocity versus time graph. Let's just try to figure out how our acceleration versus time would look like. So to start with it all, it's always good to have your x and y coordinates. X here is the time, and y here is velocity. So you're measuring velocity in meters per second and time in seconds as well. You are given, say, some graph in v versus t, and you have a graph of v as a function of time. And let's say our graph looks like that, that, and that. So let us give those, let us define what this plateau's dimension is. So let this be 0 second, this be, say, 5 seconds, this be 10 seconds, and let this be 15 seconds, this part there. On the y-axis, or on the velocity coordinate, you could define this as, say, 5 meters per second. So let's try to make sense of what's really happening to the body if it chooses to go in this plateau-like manner, or if it chooses to acquire the graph of v of t as defined here. What we know from just looking at the graph is that, well, initially the body was at rest. Why? Because the body wasn't moving in time. Initially, it had a velocity of 0 meters per second, and it held that for a very, very, very small amount of time, almost for an instant. And as time progressed for the first 5 seconds, it gathered and gained a velocity of 5 meters per second ultimately, but in between that, it had many different velocities. It may have had 2.5 meters per second at 2.5 seconds. And on the third second, it might have had 3 meters per second, and so on and so forth, until it reached 5 meters per second on the 5th second, on the end of 5th second. So that's what you mean by this gradual increase in velocity. Now, once it acquired 5 meters per second, it was moving. It was moving in time constantly for the next 5 seconds, and it moved with a speed of 5 meters per second, and that is what I mean by this plateau. So at this point here, we have constant velocity. So constant velocity vector, constant velocity in just in terms of v, works fine. What we mean here is that the body is now moving. It's never stopping anywhere, but it's moving constant time, constant speed all throughout. In fact, it's moving constant velocity all throughout. And so it's really not changing its direction. But we shouldn't really be bothered about direction at this point, because we're only discussing motion in one dimension. So if this is one direction, the other direction is basically the arrow pointing in the opposite direction. We're really not bothered about that. What we mean to say is the body kept on moving with 5 meters per second and did so for a total duration of 5 seconds, as seen there. So it held a constant velocity till 10 seconds, till the time the clock struck 10 seconds, and after that it realized it needs to brake. And it did that very conveniently in the next 5 seconds. So I'm talking about this time interval. And it sloped downwards and downwards and kept on going down. It decreased its velocity with time, and ultimately came all the way down to 0. So at this point, on a time equal to 15 seconds, the body's velocity was 0. This is what you mean by when the graph goes all the way down to 0. So at that point, at 15 seconds, the body might have been at momentary rest. So momentarily, it might have held constant velocity, 0 velocity, and would be in a state of rest just for that instant. It may have developed a different velocity later on, but we're not bothered about that, because we only draw the red line or the graph of v of t up to 15 seconds. We're not really bothered about what happens later on. So with that information in mind, is trying to find out what acceleration versus time would look like. So, like again, we would have our acceleration versus time graph there, and that should be acceleration. And let's discuss once more what the units of acceleration is going to be. So remember, position was x, and we were measuring it in meters. Velocity came out to be a derivative of acceleration, and so that meant you're talking in terms of meters from the numerator of x divided by seconds from the denominator dx. So therefore, the velocity came out to be a physical quantity measured in meters per second. Acceleration, as I've already defined, is the derivative of velocity with time. That means the units that we should be talking about would be the units of velocity in the numerator, so that's meters per second from there, and the units of time would be seconds. That means now the units of acceleration come out to be meters per second square. So that's how you get the units of acceleration. So let us have that here as well. What we are measuring on the y-axis is acceleration, and we do that in meters per second square. Time, as we have done before, would always be measured in seconds, because we don't want to deviate from our chosen norm. Right, so let's work out what acceleration would be like. Let me get rid of the unit analysis for the moment and begin with our discussion. All right, so for the first 5 seconds, so 0 to 5 seconds, if you see what's happening to velocity, it's constantly increasing. And as we have defined that acceleration is a rate of change of velocity, that means you have acceleration. If there is a change in velocity, you have some sort of acceleration. Is there a change in velocity over the course of the first 5 seconds? Well, yes, there is. Initially, the body was at 0, and it came up all the way to 5 meters per second. So there is a change in velocity. But there is also a change in velocity in time. That's a more important concept, the fact that it's changing in time. So the acceleration would therefore have been the slope of this line. And what's the slope? Well, the slope is the height divided by the base. Since this is a straight line, it holds a constant slope throughout its duration, or throughout the duration of 5 seconds. So the slope in 0 to 5 seconds comes out to be, well, this height, which is 5 meters per second, divided by this space, which is 5 seconds. So we're actually dividing 5 meters per second by 5 seconds. So if you notice, what we get is 5 goes by 5, it's just 1. What we get is 1 meter per second square, because the seconds combines with the seconds in the denominator, so it can be 1 meter per second square. And this means that that's the acceleration in the first 5 seconds. So in the first 5 seconds, if you plot it on time coordinate, well, if this is 5 seconds, this is 10, let this be 15, this be 0 seconds, that is. For the first 5 seconds, the acceleration of the body is constant at 1 meter per second. So let us plot 1 meter per second square on the y-axis. If this is, say, 1 meter per second square, then we must hold this value all the way throughout the first 5 seconds. There you have it. That's your acceleration of 1 meter per second square. All right, so now that we are done with the first 5 seconds of analysis, we should move on to the next 5 seconds. The next 5 seconds would involve the motion from 5 seconds to 10 seconds. And if you look into that, if you want to calculate the acceleration in that time interval, you would have to take the slope, or calculate the slope of that line segment there. So the slope of that line segment would therefore be the rate of change of velocity, and that should encapsulate if there is any change happening in velocity. What we see from the graph is it's constant. So that gives us a hint that if it's constant, there is no change in velocity, let alone change in velocity in time. So if there is no change, that must mean that the slope must be 0, or the fact is the acceleration must be 0. And you can also do a more thorough analysis of this constant parallel line to the time coordinate, and you would notice that it's not really rising in its height, even as it's moving in time. That is to say, this is in fact a triangle, a very, very, very small triangle with a minuscule height, or a 0 height, and a constant base. So that base is, say, b. Then, therefore, the tangent of that angle would be, tangent of theta would have been 0 by b, or basically 0. That's just a more mathematical way to go into that. But from our previous discussion, it's obvious that since the velocities are changing, the slope should not be a non-zero value. That is to say, it should only be a 0 value. So the slope, therefore, would be 0 meters per second square, and that would be the same as the acceleration. The slope is, in fact, the acceleration. Therefore, if you want to plot that now, what we get is in the 5 seconds to 10 seconds interval, the acceleration should have been a constant at 0. So it's always nice to also connect these lines by, say, dotted or dashed lines. So what we know so far is that for the first 5 seconds, this body was accelerating at 1 meters per second square. For the next 5 seconds, it held a constant velocity, and hence a 0 acceleration. This means it's having a 0 acceleration. So with that in mind, what we can do is we can move on to the next set of 5 seconds, the 5 seconds belonging to the period of 10 seconds to 15 seconds. Let's calculate what the slope in that case would be. The slope in that case would be the motion in the y, which is this height, divided by this length. If you look into this height, well, this height is nothing but 5 meters per second. But if you see that the slope goes down, so this length here must be measured in with the sign included, and that should make this height -5. This distance here would be 5 seconds because you're subtracting 10 from 15 in order to get this time interval. So the slope in that case would be -5 meters per second divided by 5 seconds. That is to say that we get a slope or an acceleration of -1 by meter per second square. So therefore, if we want to plot the acceleration in that case, we would have to mark -1 on the acceleration coordinate and hold that value for the time interval from 10 to 15 seconds. So let's try to do that. That is, if this be -1 meter per second square on the acceleration coordinate, And notice the fact that I'm drawing it in the negative direction because the value that I want to plot is negative to the value that I had before. That was 1. What I'm doing now is I'm plotting -1. So now that I know where my -1 is going to be, all I need to do is hold that value for the interval of 10 to 15. So I'm going to draw a straight line right there and connect these line segments by dashed or dotted lines. So this means that the acceleration basically holds constant for intervals of 5 seconds, but changes drastically around 5 and 10 seconds, and basically decreases. So we have constant acceleration from 0 to 5 seconds of 1 meter per second square. We have zero acceleration, or 0 meter per second square, in the interval from 5 to 10, and we have acceleration of -1 meter per second square in the last 5 seconds that we want to consider the motion of the body for. So that is what it means in order to get an acceleration versus time graph for the velocity versus time graph of a body showing this characteristic of its motion. So that is how you would get A versus T, or acceleration versus T, from V versus T graphs. Now, like we did before, if we know what V versus T is, and we want to find out what acceleration versus time would look like, all we had to do was to evaluate the area of the graph under A versus T. So the way to go from V versus T to A versus T is to take the slope. And if you want to, let me write it with a white pen, if you want to go from if you want to go to A versus T from V versus T, you need to evaluate the slope. But if you want to go back to V versus T from A versus T, you must evaluate the area. That comes out from the first fundamental rule of calculus, that slope and area are the opposite actions that you can perform in a function. So if you think about the net area in the first 5 seconds, we should get what happens to the velocity for the first 5 seconds there as well. And if you do that for any time interval or any time period, you should get the change in the velocity accordingly. So let me do that as well. Now that we know how the body goes in terms of its acceleration, let us try to retrieve V versus T graph from the graph of A versus T. So imagine that you only have this piece of information at the moment, and we would try to see if the area or the net area that we calculate from this graph matches what we intend to get in V versus T. All right, so let's evaluate the net area in 0 to 5 seconds. Net area in obviously from A versus T graph. So net area in 0 to 5 seconds would be the area of this. Everything is positive, that is to say all the acceleration is positive throughout the first 5 seconds. That means the net area would be positive. So what is the area in fact? Well, I see a base of 5 seconds right there, and I see a height of 1 meter per second square. If I evaluate the area, that would be base of 5 seconds multiplied by 1 meter per second square. Cancel the seconds out of the second square, and I get plus 5 meters per second. So this net area would mean that my velocity would have changed by 5 meters per second over the time interval of 5 seconds. So let's see if that's the case in our original graph. Well, I noticed that at 0 seconds, the body was at 0 meters per second, and at 5 seconds, the body was at 5 meters per second. So the difference indeed comes out to be 5 meters per second here, minus 0 meters per second there, or the difference comes out to be 5 meters per second. 5 meters per second is exactly the same as the net area that I get from my A versus T graph. So that means it is encapsulating the net change in velocity. That means this 5 meters per second does take into account, or does reveal, the net change in velocity in the 0 to 5 seconds time interval. So this is what you mean by evaluating the area. Let us try to now take into account what if there is any change in the next 5 seconds. So net area in 5 to 10 seconds. So looking back at your A versus T graph, you see, well, from 5 to 10 seconds, the area would be this. The area is very small. In fact, the area is 0 because the acceleration is 0. What I considered as 1 here as my height, the height here is 0. So the net area comes out to be 0. If the net area comes out to be 0 in the 5 second, 10 second time interval, what this tells us that the velocity should not have changed in the v versus time graphs. So let's see if that's the case back again. Well, indeed, it turns out to be the case, because from 5 second to 10 second, the velocity was held at 5 meters per second, and hence you had constant velocity or no change or no net change in the velocity during that time interval. So this does take into account that there is no change in velocity because of the fact that there is no net area under a versus t graph. What about the last set of time, the last interval of time? So net area in 10 second to 15 second time interval. In that time interval, we find that the area is this, but the area takes into account a negative height of 1 meters per second square, or negative 1 meters per second square. So that height is what we should consider. So that would be negative 1 meters per second square multiplied by this length there, which would be 5 seconds. So the net area comes out to be negative 5, wait, that should be 5 seconds. It comes out to be negative 5 meters per second as the net change of velocity. Let us see if the velocity indeed changed by an amount of negative 5. When I say negative 5 as opposed to positive 5 that I got there, I mean that the velocity must decrease because I have a negative sign there. So let's see if the velocity decreases by 5 meters per second in the v versus time graph. Well, indeed it does decrease, because here at 10 seconds, the velocity was at 5 meters per second. And finally, the velocity came down to 0. So 0 minus 5 meters per second is the net change in velocity, and that does come out to negative 5 meters per second, or the area that I evaluated in that time interval. So this is how you would talk about the velocity versus time. Now, I would end this video on a very key note that, say we consider different time intervals rather than the 5 time intervals that we considered so far. Let's suppose we consider a time interval of 0 to 15 seconds. So it's to take into account many different areas. So the net change in area in the time interval of 0 to 15 seconds. Let's see if that matches with what we see in the v versus time graph. So back again to a versus t graph, let's calculate the net area, or basically the net area. So the net area would be area of this plus area of this plus area of this, including the signs. The first area was 5 meters per second. That was this area right there. The second area was, well, 0. That was this area there. And the last area, or for the second area, you could write that 0 meters per second. And the last area was this area. Since it was below the t-axis or below the x-axis or the horizontal line, that area was negative. And that area came out to be negative 5 meters per second. So what we have is the net area comes down to 5 plus 0 minus 5 meters per second. And this comes down to, well, 0 meters per second. So this means that if you consider the motion from 0 to 15 seconds in the acceleration versus time graph, and you find that the net area is 0, that means the net change in velocity must be 0. So we must hope that the velocity changes by nothing over the interval of 0 to 15 seconds. Let's see if that's the case. Well, initially the velocity of the body was 0. It was at rest. And it went up, but at 15 seconds, it came all the way down to 0 again. So that is to say that the velocity of the final 15-second time interval was again 0. So you're left with a situation of 0 minus 0 meters per second as the change in velocity, which does come out to 0 meters per second. And so that does indeed match with the net area that we calculate from our A versus T graph. So this is how you work out the velocity versus time graph from the acceleration versus time graph, or for that matter, how you work out A versus T graph from V versus T graphs by calculating the slopes. So I hope this video made sense, and I hope it introduced you these ways of thinking about graphs and how you can interpolate and talk about different graphs just by knowing the fact that one of them plots a derivative of the other function. Like in this case, acceleration was in fact the derivative of velocity. So we ended up taking the slope. And if we wanted to go back, we had to calculate the area. Simple as that. It also depends on the interval of time that you're talking about. In the case of the net change from 0 to 15 seconds, we found that the net change in area was 0 because initially the area was positive and finally the area was negative. They cancelled each other out, and so we got a net change of 0. And that did show up in a v versus t graph when we realized that the initial and the final velocity of the body during the time interval was in fact the same. And hence, there was no net change in velocity altogether itself. So I hope this video made sense, and I hope it urged you to realize the importance of these graphs as well, and how helpful they can be from in order to get a variety of information out of the motion of the body. So all the best and have fun.